Ihr hört die Erium Podcast, der Data Science und Machine Learning Podcast für Studienabsolventen und Young Professionals.
Today's guest on the Erium Podcast is Dr. Danko Nikolić. He is head of AI and data science at evocenta GmbH and is guiding a team in developing an AI solution for customer support. Before that, Dr. Danko Nikolić worked as a consultant in AI and data science and has also headed AI development in one fintech startup in Frankfurt. His passion for AI is combined with his equally intensive passion for brain research. For many years, he headed a lab at the Max Planck Institute for Brain Research, applying machine learning algorithms for reading brain signals, for reading thoughts. Dr. Danko Nikolić likes to work conceptually and practically. He likes to address a problem first from a conceptual perspective, which machine learning theorems apply here, and then practically, how to make the machine work. Nowadays, when his profession is AI, his main hobby is neuroscience. Dr. Danko Nikolić continues to do research and write papers out of pure passion. In his free time, he likes to ski.
Welcome to this new episode of the Erium Podcast. My name is Theo and my today's guest is Danko Nikolić. Danko, I'm very glad to have you in the podcast.
It's my pleasure to be here.
Let's dive directly into medias res. We heard in the introduction that you have a very diverse background. You are at home both in science as well as in the application of machine learning and data science. Before we dive into that, could you please, again, explain in a little bit more detail what your current employer, evocenta, is doing so that we get a feeling about your today's everyday work life?
So evocenta is basically a customer service company. And it does services where it has lots of agents, and their customer companies simply call when they have problems on computers, and the agents help solve the problem. Something doesn't work on a computer, and then the agent fixes it, installs new software, whatever. Right?
Okay.
And this is a kind of a problem that takes lots of time from the side of the agents. Wastes lots of time from the side of the customers because they have to call, wait on the line, get the reply, and then maybe the agent doesn't know the answer because the computers, they are complex. There are so many thousands of different things. So we figured this is a problem that is most ripe to be automated by artificial intelligence. And that's what we are doing. We are developing an AI system that will be able to help solve these problems. Right? So when you call or write to your customer support service, you would first hit an AI, and then the AI would try to help you first. And only if AI is not able to help you, it will pass the problem on to agents. So it saves your time as a caller, as a user. It saves agents' time as another side of a cost of the company that they have to pay for these people. Saves everybody time, and everybody should be happier. And problems should be solved faster.
All right. And even if the AI is not able to solve the problem, maybe, or I assume that there is a pre-classification done. So maybe the case then is already forwarded to the best matching real agent to solve the problem, right?
Yeah, absolutely.
So you can do a lot of pre-processing there.
You can do lots of pre-processing in this sense that you decide to whom you will solve the problem, but also you could guess what the problem is, although you're not 100% sure. You guess, AI guesses, and then proposes already the solutions to the agent. Right? So it could help agents quite a bit. And they have to maybe sometimes just make final decision. Yeah, that's right. Go. And that's it.
Let's jump even deeper into this use case and this product in a minute. First of all, let's step one step back and let's discuss your role. If I understood it correctly, you and your team, you are working and you're developing this AI component, so the real heart of this company. Could you explain a little bit about more about your role? So, what's your very personal responsibility, and how does your team look like?
Well, my responsibility was to put the team together, or at
Mm-hmm.
least part of the team together, and to make sure basically that the whole thing works at the end. Right? So
Okay.
if it doesn't work, if there's a problem at the end, I'll blame it on myself. If there's intelligence problems at the end, I'll blame it on myself. So I think I've seen many AI projects fail for the reasons that at the beginning, when you do some first proof of concept, everything looks good, very promising.
Mm-hmm.
But then when you start tackling real life data, real life problems, suddenly it doesn't work so good and doesn't want to learn, doesn't want to train, doesn't want to improve. And that's what is my main worry. And this is what I keep saying, that this is my main responsibility, to prevent that this happens at the end. So that my main problem that I'm tackling is making sure that whatever we do now scales well, but
Mm-hmm.
scales well in terms of intelligence, not scales well in terms of number of customers. That's
Okay.
the easy part, right? Scaling well in intelligence is the hard part, and that's what I'm trying to ensure that we do well.
Okay, you say this is the hard part. Also for you personally, is this the biggest challenge for you? Or is there something else where you say, okay, actually, I know quite well how to scale the intelligence part, but there is another problem maybe involved in the process, or maybe it's team thingies to solve?
Well, there's always other issues, hundreds of other issues. And 1 month one thing is the problem, next month something else is the problem, and it's like
Yeah, indeed.
you never know, and there's always some fire somewhere, and it's normal life, right? But so if we go back to scaling intelligence, no, I mean, I have pretty good solutions and pretty good ideas, but nobody knows really how to scale intelligence effectively, right? We don't, as a field, we don't have good solutions.
Mm-hmm.
Even the problem is not very well recognized as a problem, and there's very little literature on that topic. So that's something that still needs to be researched from the academia side, something that has to be worried about. And I have a passion for that comes from my neuroscience background, because human brain is actually very good in scaling intelligence. So by studying human cognition and the biological brain, I got some sort of a thing for that, a thing for scaling intelligence. And so, and I could also say that this is a problem that's most fun to solve. All the other problems are less fun to solve. And if you have, some sort of, access to server, you don't get access to server because of some administrative problem. How can this possibly be fun?
Not at all.
Not at all. But it could hold you up for weeks until you resolve this and get proper licenses and all that. So yeah, I mean, every work should have fun part and should have the necessary part. So, but then also, these other problems are in principle solvable. We know that they are in principle solvable. So they are not as challenging at the end. They are not really challenges. The problem of scaling intelligence could be, there are cases where, companies failed quite, in a big way for failing to scale the intelligence. So that's challenging and not solved. It's interesting. It's fun, and yeah,
All right.
that's what we do.
Um, uh, Maybe let's make this even more specific. Scaling intelligence. Do you have an example where you have maybe an application or a use case where you can take us through this journey with a small starting point and then maybe intermediate steps to a solution where you would say their intelligence has been fully scaled?
Okay, let's see this example.
Mhm.
Let's say you develop a deep learning network to distinguish cars from animals. You have a bunch of pictures of cars, but a bunch of pictures of animals. You train the deep learning network. And now, because it's a simple task, you have just two categories. You don't need anything complex. Like a relatively simple machine learning model will do it. You don't even need deep learning for two categories, probably. But now you want to add third category, fourth category, fifth category. That's intelligence, right? You want to keep the same accuracy. Let's say with the two you got, I don't know, 95% correct.
Mhm,
Now you
mhm,
want to
mhm.
keep 95% correct with third category, fourth, fifth, sixth. That's scaling that's increasing the intelligence of the system. And now the question is, how many resources do you need to increase the intelligence? Like if you double the intelligence, if you go from two categories to four categories, is it enough to just double the resources? Or do you need even more than double the resources? And the resources are computational power, amount of memory, the number of parameters, the size of the training data set, and so on and so on. Right? And all the data we have, all the studies we have, all the research we have shows very conclusive image, a very conclusive answer to this question. It's that deep learning very poorly scales intelligence. It's actually a power law function, right? So
Mhm,
to
mhm.
double the intelligence, you need more than double the resources. Right? That's a problem because it's not sustainable.
Indeed. And how does then the process look like that you use? Because it's isn't this kind of related also to the problem of complexity in software engineering, where you could think of all scales that might occur in the future and then get stuck in the details in the very beginning and not getting done anything at all. So the same could apply here, right? So even if you start with the two category classification, if you immediately then jump into a very sophisticated algorithm and use it because you expect to classify like 35 or 50 or 100 categories in the future, but then you not even make it work for two categories, from like an agile perspective, this would be worse compared to using a very simple approach that manages to classify two categories. And once that goal is achieved, you try to evolutionary improve the algorithm to make it work for three and then for four. But of course, and that's like the opposite side of the coin. If this simple algorithm hits a boundary at some point, so let's say there is a theoretical limit of five categories, and then you can mathematically prove that more isn't doable anymore. Of course, then this is a problem. Yeah, and I see that this is like a feel of tension. And I would be interested, how do you manage then this process? Like not getting stuck into details very early, but also not hitting a wall after the third or fourth iteration.
Yeah, good question. Um, so where to start answering this question? So I mean, let's see first how it happens typically in the process of developing of app. What people typically do, that they do for the small one, and they
Mm-hmm.
call it some sort of proof of concept or
Yeah,
maybe
yeah, right.
even MVP, and minimum viable product. And they say, okay, look, proof of concept works for two categories. Now we could just principally expand it, and then let's go expand it. Let's get more money, more funding, and then we'll make it bigger and so usually people start with small things and try to build it up. But and then if they fail, where they fail is that this algorithm or whatever strategy they took doesn't really want to scale.
Mm-hmm.
And you mentioned mathematical proof. Typically, it's not possible to make a mathematical proof, especially not in deep learning kind of problems, because the mathematics behind it is way too complex. Nobody
Mm-hmm.
understands it. So it's just, unfortunately, you have to experiment.
Mm-hmm.
And that's really unfortunate, because if you had a mathematical proof, then you could easily calculate, and it's like, okay, we will not be able to reach it with this strategy. Right? And what people do, they experiment and sometimes succeed, sometimes fail. Now, your question, so that's what you typically do. Now, what the strategy that I think is the right strategy to do is to look, not when you do your proof of concept, you don't only look what accuracy you got with your proof of concept. You already have to assess your scaling rhythm, your scaling curve. Right?
Mm-hmm.
So
Mm-hmm.
you could take, if you have limited data set that size, you could also train your model with half of the data set, quarter of the data set, and so on. If you have 4 categories, you could also train it for 2 categories, and so on. And you could plot and see what the curve is. And then you could think, okay, how many categories you may need it. Extrapolate this curve. Keep in mind it's a power law. And see which numbers you get. Right? I once did such numbers for the human mind. I've got some estimates of how many categories a human mind can distinguish and things like that. And then numbers were just mind-blowingly huge. It's just completely impossible to do that. Like, the smallest one you get is 10 to the power of 25, and more realistic 10 to the power of 40 or something like that.
Wow.
So it's like, like the number of atoms in the universe almost, or something like that. So it's the deep learning wouldn't work for human mind, but it could work for the problems that you are solving somewhere else, right? Now, this still doesn't answer how you fix the problem. This only answers maybe how you detect the problem. Right? And I found out what is a fixture to the problem. How did we in the past, create algorithms that actually solve some problems without breaking up? And the answer is basically you have to be creative, intelligent, and figure out an algorithm that is perfectly suitable for that particular problem that you are solving. And then this algorithm then is going to scale well. So if you design an algorithm that's designed just for that problem, this is going to be the best scaling algorithm, right? It will have the best scaling performance. Deep learning is on the other side. Deep learning is very generic. You could
general purpose AI. Yeah.
You could just train anything, but that's exactly the price you pay. You can train it to do almost anything, but as a price to pay is huge amounts of data and a very poor scaling. Right? So you have to basically turn things around and reorganize the architecture of your AI such that it's suited just for that particular. You have to make it more specialized, a lot more specialized. And by making it a lot more specialized, your scaling curve will just go down. It will still be probably power law, but the exponent will be much smaller. Right? Could sometimes be even a linear. It's also possible. So that's what you need to think. You need to analyze the data, think about it, and think how to reorganize your algorithm such that the scaling is right. So,
all right. I think this is extremely interesting. It reminds me of an approach that we used at Erium, not with this big understanding of scaling complexity, but we just had the problem that the data was not enough to train a not informed model and not about the use case informed model. And then we started to build a Bayesian graph, actually, about the parameters and how they are interdependent to each other. And this very informed model, it can only be used for the specific use case, but because it has a lot of inherent structure that reflects reality and the use case that should be solved, we were able to reduce the amount of training data needed. And now this model is very robust and scales well with respect also to disturbances in the data. So it's like a real life example of what you just described. But I think this was like a lucky shot, because we had from our PhD studies, we had Bayesian networks at hand and all the Bayesian statistics. So this was like by coincidence, maybe then a good tool to do it. I'm interested in, so could you open your toolbox maybe a little bit for us? So what possibilities do you see? Because I totally agree with, make it specific, tailor your algorithm towards the problem. But on the other side, if I now import Keras in my Jupyter notebook, okay, how to do it actually?
Oh, you mean how to code it into
no. How to tailor make your algorithm towards the problem if you're not using, so the way I know is Bayesian statistics and Bayesian networks. What alternatives can I use for that? Is it like feature engineering maybe, or I've no idea.
Feature engineering is a part of the process. Of course, feature engineering helps, but it's not the ultimate solution.
All right. Yeah. Would have wondered.
So, I mean, the ultimate solution is the ultimate start is analyze your data, right? Do the analytics, look at the distributions, the correlations, ask questions. And every time you do analytics, you get some answer. Every time you get an answer, you think about like which kind of equation would describe this. And then this idea may ask a new question. Then you analyze data, ask new question. You ask yourself which kind of equation or whatever I know in mathematics and statistics, in machine learning, which one describes this problem best or well, whatever I see in the data. Whatever ideas you have, they're probably going to fit your or be a more suitable model than any generic model. Now, based on these equations, start building your model. You can also, if you have some amount of data set, you can feel free to keep some things unclear. So leave some parameters, to gradient descent to learn them. Right?
All right.
But put as much as you can on these equations, right? And then try out in small data sets, quick learning, approximate them. You should keep in mind that every analysis you do is, in a way, a micro modeling process, right? Because to analyze something, you have to apply some sort of model to calculate your result, right? If you just use correlation, it's still a model it's a very simple model that you apply to two variables and you get your fit result, right? So you basically, when you analyze the data, you're looking the pieces of your future big model, right? And those that have get high numbers, use those, right? Be creative, and eventually that's how all the existing models have been created. Anyway, nothing else. Somebody has analyzed the data, looked at them, and thought about, okay, what in mathematics that I know of reminds me of this, could describe this, what I see. That's how everything that we have today has been built. So just repeat this process. As opposed to just blindly going and having like, here's my data, I have my preferred algorithm, which is algorithm X. I'll just feed them in, whatever comes out, that's the result.
Yeah. Let's use a random forest because we always do.
Exactly. And it's cool.
Yeah, exactly.
Okay, so,
because of reasons. Yeah.
So don't have favorite machine learning algorithms.
All right. Let's look into the past. If you look back, maybe also from your time in neuroscience, do you have like maybe one project that was the one that where you would say this project was the most successful one?
Wow, you have lots of projects that were many failed, many succeeded in different ways. I had, some scientific projects that were just scientific insights. So you write, at the end papers about some conclusions about how the mind works.
Yeah.
I had projects that built, some sort of code and machines that worked. So there's some success, different types of successes.
But then let's make it specific. So maybe your personal success metric, to phrase it like that. How does it look like? Is it insights, maybe?
Insight, yeah, I would say insight.
Insight?
Yeah, for me, it was, as a scientist, yeah, that's probably what you want to have is insight.
Yeah.
So probably the most successful one that produced most insight for me was my work on one theory, a cybernetic theory that I tried to fit to behavioral and brain data. And I named this theory practopoiesis.
Okay, please explain.
So practo means action.
Okay.
And poiesis in ancient Greek means to create something. And there's an old tradition in brain science that the idea that the brain and the living systems create themselves. That's where their intelligence is, right? Like at the beginning we were all just a single cell with genome, and then this cell interacted with the environment that divided into two cells and so on, and the whole organism came out of it and so on. That's the poiesis, the poetic process, right? Now, by acting with the world and interacting with the world, that's how it happens. So the idea is that also our intelligence, our brain does exactly the same thing. All our knowledge, all our experiences come through this interaction and poetic process. But then my biggest insight came that the same is the truth for each thought. So for each perception, for each decision. Okay. Decision is not just a calculation like in machine learning, where you put input and output, spit out the output. It's actually interaction with the environment. For us to perceive something, to decide, to come up with idea, to think, to be awake at all, we have to do this poetic process, acting on the environment, getting feedback, acting feedback. Every thought, every perception is this loop going on. That's maybe my most, I would say, successful internally project that one day may even result in some new type of artificial intelligence algorithms. But we are probably quite far right now from that.
Yeah, looking at today's algorithms, I can agree.
Yeah.
And looking at the other side of the coin, because as we heard in the introduction and came out of the conversation so far, you're familiar with both worlds, science and the application. What was the use case where you managed to operationalize maybe an algorithm, a machine learning system, or maybe an AI system that maybe not even had to do anything with machine learning at all in the most scaled way? Like now scale, not in the intelligence way, but in the application way.
Maybe one interesting example was when I was working for a fintech startup, and we wanted to build an AI to manage a portfolio of cryptocurrencies, a saving portfolio of cryptocurrencies. Now, what you would do, like straightforwardly, you would pick up some algorithms, put the data, train the data, try to predict the trends and changes in prices. Yeah. But this was impossible for the same reason you explained. We had very little data. Right? The history of cryptocurrencies is very short. The number of cryptocurrencies in the world is It's very small, and they were all super correlated. Right? So what did they do? So you had to go back down to something that was simple, like your example with Bayesian inferences. Right? But we couldn't do Bayesian inferences, so we had to come up with something. So and that was where I started combining the scientific skills and practical skills. So on one side, we had to produce something to work and to do a good job. On the other side, we had to think like scientists and analyze and understand what's going on. So what we did was the following: we took like the textbook on financial mathematics and read about the known phenomena in the classical financial mathematics. So in the market of stocks, options, money, maybe fiat money, maybe a little bit, but mostly.
Yeah, there's a lot of theory there. Yeah,
lots of theories, lots of mathematics, tested theories, and so on.
Yeah,
but we had, and then we had some data. We had enough data to ask questions like, does this rule apply in cryptocurrencies? Does this property apply to crypto? Does this one?
Oh, nice.
And we could identify which ones apply, which ones don't. And if they don't, then we could describe them with, whatever we see the data. We just change the theory from whatever we see the data. Right? And based on this analysis, we build a model. Right? The model would just then take the history of cryptocurrencies, the current state of the market, apply this new theory under quotation. It's not really it's like old financial theory with some twists that are specific for crypto market. Right? Apply that, do some calculations, and spit out the predictions. Right? It was completely new algorithm. It like never existed before. It never existed. We combined all kinds of some things from numerical mathematics, some things from geometry. We needed to work in three-dimensional spaces. Find some tangents to some clouds of distributions of points and things like that. And at the end, it worked very nice. It works very beautifully, very reliably, as you described, very reliably. You could trust it that it's going to make good decisions. And it was running for a couple of years. Very good. Sometimes it would make a weird decision that we would go jump back, check by hand what happened. And every time it just made the right decision. Every time.
Okay,
right?
Okay. Even it was weird. It was right.
Even if it was weird and it was made the right decision. It's just that the market was weird. The crypto market was crazy. And then the machine decided to do this weird thing because the market behaved crazily. Right? So it was pretty good. It was pretty good. And I recommend doing it to everybody who has the patience to do it.
And now you made me super curious. So maybe you can share, maybe not because of confidential NDAs and confidentiality, but can you share a surprise? Because you just said that some rules from classical financial theory did not apply. So do you?
One very important thing was that so in the classical financial theory, you look at the return and volatility. And volatility is your standard deviation variance of some changes in the prices and so on. Now, what ended up being very important in the crypto market, in addition, was volatility of volatility. So crypto market was not only very volatile, but its volatility was extremely volatile. In other words, the crypto market had periods when it was kind of stable.
Yeah.
And then jumped high, up. Then the crazy thing happened. Then again, stable. Usually, after this crazy stuff, it would just go level up. And it was relatively stable. And then again, crazy, something happens. Some journalists are writing about it. Who knows what happens in the background. And then again, stable, or it goes really crazy down, but then again, stable, and so on. And different rules applied during different levels of volatility.
Okay, understood.
Right? So we had to. That's why we had to work in three-dimensional space, like all the classical finances work in two-dimensional space. Like you plot return versus volatility. Right? We had to plot return versus volatility because you had different shaped clouds during different times, and you had to navigate through this space. Yeah. There's actually whoever wants to learn more. I think there are 2 talks of mine that don't reveal everything, but quite more than what I said now. That can like just Google it on or YouTube it, search for it on YouTube.
We can put those in the show notes. Yeah, that would be nice.
Very good.
Yeah.
Very good.
Yeah. All right. So I also read that you're one of the members of Robots Go Mental.
Mm-hmm. Yes.
And the claim there is we make deep learning learn from small amounts of data.
Yeah.
And now I wonder, what's your approach there? Is there, again, one more approach in Robots Go Mental, or is it actually the approach that you just described of really carefully looking at the equations and then building the deep learning system according to the equations? Or is there another twist in Robots Go Mental?
There is another twist, but it's the same principle. But the twist is that it's not human who is looking into it, but it's a machine who is looking into it.
Oh, all right.
So you first have a large data set.
Okay.
Where you can look for the rules. And the machine finds the rules and then applies them afterwards when it has a small data set to learn. So the machine learns what to look for, let's say. It's kind of learns to learn effectively. Right? So we did examples with MNIST data set. So you could, in an MNIST data set, you have enough data to train quite well, to reach quite high precision with recognizing handwritten digits. And there's also MNIST for letters. You can also do quite well with that. And but we could also train, like you have a deep learning model, then on top of a deep learning model, we have another level that learns how to effectively learn new types of letters or new types of digits within this space of handwritten digits. So what is relevant, what is not relevant for learning? And if you have a large data set, you could just try and figure out what these things are. And then you get a new data set, new example. You make up a whole new writing system. You can make up your own writing system and have just one example, right? But as a human, I would know, like if I make up new letter for you and I say, okay, this is a new letter A and looks like, I don't know, weird, like a ship. You would already know the next versions of that, like how
natural variations.
You would already know how italic version would look like. You would already know what a bold version would look like. You would already have a guess, what was written in a hurry. Or you could even look a handwriting system of a certain person. That's okay. That's how this person writes. Then you could guess how this person would write this new type of A that looks like a ship, right?
Because I understand the process, how the letters are made.
Exactly. You understand the process at some like much higher level than our system, but our system also understood it under quotation, understood it at some level, right?
All right.
So we could give it single example, and it could learn quite well. Right? It could learn quite well all these variations. Right? Now, this is called one-shot learning in deep learning, and there's many different approaches to one-shot learning. So we could say that we just have one of multiple different approaches to one-shot learning, which has, again, its own advantages and disadvantages compared to the others. But it's original. It has never been done before, as far as I know. I don't know, maybe, but not. So basically, that's what we are doing.
All right, very interesting. Let's make a small break here and focus back on you as a person. Could you explain a little bit I hear that there is a big fascination. Yeah, when we discuss artificial intelligence and algorithms, where does this fascination come from?
I think, if I go back into my childhood, I remember situations where this fascination should have come from. I remember as a kid watching some sort of science fiction movie, and some person talking to some box with two lights and discussing with this person something, and I asked my father, like, what is that? And he said, oh, that's computer. I was like, oh, wow. Thus I thought as a kid, computers are intelligent machines. And then, when I grew up, I got my hands on the computer, and boy, was I disappointed.
Oh,
There
man,
was
just a
nothing
set of
like
rules,
this
right?
movie. When I
Yeah,
was
yeah,
a
yeah,
kid.
yeah.
So, then I was like, let's, no, I was like, but thinking like, what would it really take to make a computer be intelligent as a machine? And I think this is where it came, like really this, dreaming as a kid of intelligent machines, robots, and all this. Like, I don't know, many kids, but sticking with it, and then being disappointed at some point that computers are not doing it, and trying to understand why it's not working, what is missing. And this led to my interest in cognitive neuroscience, in studying how the brain works and all that. So it's all somehow connected.
Do you think with the current path of technology development, we're gonna reach a point where we maybe have this phase transition from, okay, it's just a gradient descent, training a regressor, to really what one could call a strong AI, maybe with quantum AI? Or don't we even need quantum AI for that? So what's your perspective on that?
Yeah, that's a long story. I have lots of opinions, but lots of questions and lots of ideas. Uh, well, I mean, the way how we do it today is not enough. It's definitely not enough to reach kind of levels of intelligence and flexibility that biological intelligence can achieve. That's not the same. These are different things, and it's not gonna be enough, right? So just having a bunch of parameters and a gradient descent, it's not how it works in humans. It's helpful, it's practical, it's a part of the story, but maybe less significant part of the story. There's something big missing that we are still missing, and also people are working on it, trying to figure it out, and it's hard, to figure it out. And we need to figure it out to have something called strong AI. And the strong AI, I think it's important to define what is strong AI, because in the world there are two definitions. The first definition came from Searle, the philosopher, who basically defined it as AI, how biological systems do it. So he assumed like that his dogs were strongly intelligent, and then the second one that kind of ignored this and redefined it as human level intelligence, which is, I think, the second one is, I think, misleading and problematic, because this assumes that we can kind of directly jump to human level intelligence and skipping over dogs and cats and bees and whatever. And we can't. We have to, I think, go through all that. We have to cover all that before we
All
can
right.
get
Okay.
to the human. So we have to aim for the strong AI as Searle has defined it originally, not as it has been defined later. Right? And that's why we have to study the brain and try to understand. And we have to understand how the brain works, how the nervous system works. And we're still not there. We still don't understand it.
Totally agree. Yeah. I'm very interested in if my kids will experience strong AI on a human level. So, very looking forward. Let's go back. As far as I understood it, your work is very creative, very scientifically driven. Yeah. Thereby, what I'm interested in is how do you decide how to lay out the roadmap of future developments? Because in science, you have more freedom than in a company. Yeah, so you have various shareholders in a company, and you have to argue why to do this and this and that. And I'm interested in how do you set up the strategy? Is it maybe a mix of creativity, but also like a metric driven roadmap, or is it completely metric driven? Maybe you could explain, or maybe you have colleagues who are completely fine with a creative, scientific approach. How does this look like? Because I'm asking this because I see that the very scientific field of data science often is compressed into the rules and the boundaries of big corporations, and then things go wrong because the environment doesn't fit or does not correspond or does not reflect the needs of data science.
Yeah. But I mean, let me just ask some questions to questions. You're asking the whole story in terms of the strategy to reach strong AI, or in terms of strategy to reach AI for some commercial purposes?
The second one. So in a very hands-on matter.
In a hands-on matter. Let me think. But first, I think it's important to know that in science, it's hard to say that you have more freedom. You have different types of freedoms.
All right, fair enough. Yeah.
You're also closed at many places, right? And it's not that in science you can do whatever you want, and that you can make a successful career in science. It's not, unfortunately, it's not how science works. Science also has its own rules, requirements, demands. Sometimes quite limited, quite pressured, and it's not easy. It's not easy either. So I would say both are limited, industry and science, just in different ways. And it's good that two different worlds exist. It's much better than having just one world. Now, in the industry, yeah, it's especially the problem with data science and AI and related things, because they have this research component, this undetermined component. You want to achieve something, you feel there is a way to there, but the way is not known. And the traditional industry, you know the way how to do it. If you want to build a new bridge, you know how to build a bridge. You don't need to do research. If you want to build a new building, a bigger building in the world, you know how to build it. There's textbooks, just read them, and you know. Now here you have to do research, because you're on the border between known and unknown, and that's where the science part comes in it, and that's why data science has the word science in it. That's the research part of the whole thing, and gradually the companies are taught to be more open to this research component, to be more to allow that, to invest in that part, to be aware that investment in this direction can produce returns, and to be aware that your competitors are doing the same, so you better be doing the same.
Yeah.
And so it's making this progress, right? Still, in practice, if you compare what academia is doing and what industry is doing, there's still a gap. There's still a gap in type of questions they ask, how far they push it, and so on, right? Nevertheless, if some of the companies that can afford it, and the only companies that can afford it are big ones like Google, Facebook, Microsoft, they go full blown. Let's put the two things together, right? So they can go for a long term product, but put on this like completely fundamental scientific like research, including writing, publishing papers, and so on. This is extremely expensive, and like it's research normally can only governments afford, and then this is research for everybody, for the entire society, not only for this one problem that this company wants to achieve. But these big companies now have so much money, and the capitalism works in such ways that they can afford to do both, and they have like whole research departments, and they can afford to have hire 100 people to work on a problem. And if one is successful and the other 99 are not, still good enough. So, yeah, that's how it works. And smaller companies cannot afford it, of course. So they have to kind of grab around whatever they can, and try to keep up. But the divide is probably going to be bigger and bigger. And yeah, that's how it is. Like, I mean, this divide is really obvious now when you look at the size of the models. Like, you remember we were discussing just at the beginning of today's discussion about this power law growth.
The power law, yeah.
That's the curve. Now, how we counteract it? By bigger and bigger models. Right? But to make more and more intelligence, we have to build bigger models, have more data, and so on, right? But as we do that, the number of people or institutions who can afford them shrinks. Right?
Yes.
So 20 years ago, everything state-of-the-art deep learning model anybody could run. Every student, university student could get a computer who could run it with a GPU. That's state-of-the-art, right? But then it wasn't, soon enough, it wasn't anymore state-of-the-art. You needed 10, 20, you needed a farm of GPUs, right? But then that wasn't enough. So you needed TPUs and all this stuff. And now you have GPT-3 and all these models that are monsters, and only a few companies can afford to have them. Like a couple of days ago, Microsoft has announced their service where you can use now GPT-3 in your codes, and it's now like available. Of course, you're going to pay for it, but
via API, right?
Via API, right?
Yeah,
of course. But the point is that only few companies can do this now. Like, it's not like a startup can say, like, oh, we're going to make GPT 3B or 4 or something.
Yeah.
You are? Sure. Good luck with that.
Yeah, I've got this workstation here. Yeah, exactly. Let's do it on that one.
Exactly. Like, you have, I don't know, $500 million just for a proof of concept. So it's stretching, and of course, this is growing up, and soon enough we're going to reach whatever even Microsoft and Google can afford to pay for, and the company and the other companies. Right? There's also a limit, and this very quickly will reach this limit because the curve looks like this, and it just grows up, and up, really steeper and steeper every day. Every time you make a progress, the next step is even steeper than the previous. So. Yeah. Why are we talking about this? How did we come to that? I don't remember anymore. But
we were talking about strategy.
The strategies.
And maybe looking at the developments that you just described from a data scientist perspective who works in not one of those super big companies. Yeah. And I just realized that I also benefited from Microsoft research because they published a paper about a very parallelized implementation of LBFGS, an optimizing algorithm. And I used it in my PhD thesis. So so this was good for me, but actually it's exactly as you describe it. So only a few companies can afford having a private university and also then training those super big models. And I'm wondering what is now the consequence for me as like a layman's data scientist? Oh, no, that's the wrong term, but like a data scientist in one of those smaller companies. Should I just accept this, or is it still worthwhile to work out individual models, but then not for those use cases that are covered by, like, for example, GPT-3? is it still worth the effort to build individual models by hand? Or should I, as I just said, just
Give up.
accept it, use the models, use the API, pay for it? That's reality. What's your opinion on that?
Oh, you definitely should build your own models, definitely, because their models are just a part of the spectrum of what can be done. Right? These are the dumb models. This is the brute force stuff. These are they take generic architectures, huge amounts of data, brute force on it, and it works. But as we discussed, like your really efficient stuff will be when you think about it, when you analyze the data, when you think about it, when you describe it with your own equations, with your own insights. It's definitely absolutely worth it. And you could beat them in particular problems. You can always, I think it's even possible mathematically to prove it, although I don't know right now how. It's just a feeling. To prove it that it always exists a simpler solution than just, whatever has been learned by a huge deep learning model that with analytics and so on, you could just reduce it down for a particular solution, for a particular problem, a much smaller, like many zeros cut out a size of the algorithm. And that's your opportunity, your benefit, your market, your something that you can bring. It's cheaper, it's more effective, and so on, right? So and you need it in the in IoT, so in the edge machines, right, where you don't have access to huge computational power. Right? Like today with self-driving cars, it's the same problem. Right? Tesla has a huge model and their supercomputer in the Tesla basement that they can do stuff that a single car could never calculate. Right? So they use this huge model to train a mini model that they can put in a car, right? And the huge model is basically creating examples, training, and so on, trying to tune this little model in the car. That is little is still big, but compared
to the one on the supercomputer,
exactly, is actually, and because that's what the car can get. This is all the car can get, right? And so they are also facing this problem, and so GPT probably, some of these things like that you want to have on your phone, you don't want to contact the Microsoft super big server every time. You want to do it maybe locally, some things. So there is a lot of room. There is a lot of room. This is just a brute force thing, and it's useful, helpful, but it's not the end of the story, definitely.
All right. So there's a lot of room in the space of solutions.
Yeah, I think so. Infinite. The space of solutions is infinite.
Infinite. All right. What a nice conclusion. Let me ask one more question. So, which advice would you give to your 20 years old self, if you could?
Oh. I don't know. I wasted lots of years trying to solve some things that didn't work out at all. Like the strategy was wrong. So maybe.
Do you regret that actually?
I don't know. I mean, it's like, when you look back and you say, okay, that's a part of the whole thing. It's a part of experience, a part of life. It's like how you learn things. Then you say no. But then if you go back and say, like, do I want to repeat this again? You don't want to repeat that either. So, yeah, I don't know. It's not like a regret, but that would be maybe advice. Maybe, another advice is not to take things seriously. And whatever you do is not so important, so serious as you think at this moment. It's like, whatever you do, you tend to think that this is the most important thing in the world right now. Like, oh, if this doesn't work, the world will collapse or something. But actually, the world doesn't care. Or there is a few of your friends and colleagues who care, but that's about it. Nobody else cares, and everything else goes on without. So yeah, just kind of take it less serious. Maybe, I don't know. like the whole AI problem. It's not so serious. I mean, I now start realizing that there are a lot more important problems in the world than AI. Like AI is the most important world problem for me, but for the real world, no, it's not really the problem. The real problems are, global warming and these kind of things, like political, the problems of social problems between, the growing gap between rich and poor, and the potential of nuclear war, too many weapons, too much injustice. These are the real problems, and AI at the end is just nerds fun.
All right, I should take that advice too.
Yeah. So being aware of it, stay being nerds, but just be aware of this.
Yeah. So like a humble relaxedness. Yeah.
Exactly. Yeah, something like that.
All right. Danko, thank you so much. It was so much fun having this conversation. I learned a lot. I hope that the listeners, the Complexity Masters, also learned a lot from this conversation. Let's put those talks in the show notes. I'm going to check them out by myself. And I wish, Danko, that you have in the future as much success as you had in the past.
Thank you.
That the failures may be minimal, but enough to learn from them. And I'm very looking forward to talking to you maybe again in the future.
Oh yeah, sure.
And wish you all the best for the rest of the week. Have a good time. Bye to the Complexity Masters. I wish master the complexity.
Um auf dem Laufenden zu bleiben, folgt uns auf Facebook, Instagram, Twitter und LinkedIn. Wenn ihr uns unterstützen wollt, gebt uns eine 5-Sterne-Bewertung auf Apple Podcasts, folgt uns auf Spotify und empfehlt uns weiter. Bis zum nächsten Mal bei The Erium Podcast.